Simon, I'm going to let you introduce yourself just in the spirit of time.
Yeah.
You have to close us down this afternoon. So Simon Payne is standing up on his feet. I know you've just had a lot of international flying. A new presenter, Combustion. So really welcome to the event for the first time.
Yeah, thank you.
And very interesting, talk to us about insights into filtration performance relating to PPE, personal protective equipment, RPE, respiratory protective equipment, and also HVAC filters. So I think something very pertinent to clean rooms and containment. So Simon, I'll hand over to you.
Okay, thank you for the introduction, Tim. So I have put together quite a comprehensive slide deck, but I know this is the last talk and I don't want to hold anyone up, so I will be breezing over parts of it. Yeah, so as I say, it's quite a comprehensive slide deck, so that's set up for people to digest at a later stage, and my email address is at the end in case anyone wants to send me questions. But I'll be covering some data we've published previously on both PPE and on HVAC filter testing. This is using a new approach to classifying particles by aerodynamic diameter. And then before I get to that data, I'll just cover some basics on filtration mechanisms and how we define aerosol particle size and the different classified techniques that are currently available. So a little bit about the company I work for, Combustion. We were founded in 1987, spun out of the engineering department in Cambridge, initially to develop fast response gas analyzers for combustion exhaust measurements. Those were using industry standard techniques, flame ionization detection for hydrocarbons, non-dispersive infrared for CO and CO2, and chemiluminescence detection for NO and NO2. But the key thing was the sampling system was designed to preserve very high temporal resolution. So we have time responses down to about 1 millisecond. So wherever there's a need to measure rapidly changing concentrations, or you're anticipating having to measure short-lived spikes in emissions, our instruments are well set up for that. And then since then, the analyzer has been adapted for ambient monitoring, air quality, and medical applications. And then following that, aerosol science instruments followed. So that includes a fast response particle sizer. And then in the last 5 to 10 years, analyzers that classify particles by mass and by aerodynamic diameter. So that's highlighted in red. That'll be the focus of this talk. So this slide just very briefly summarizes the mechanisms in play for particle interaction with filter media. So on the right-hand side, you see there's diffusion, interception, and impaction. These diagrams just show gas streamlines going around an element, a cylindrical fiber element in a filter. So with diffusion, collisions with gas molecules affect this random walk. And the key thing with the size dependence of diffusion is it's a more effective mechanism as particles become smaller in size. Then there's interception, whereby particles follow in the gas streamline but passes within one particle radius of the fiber and is collected. So together, diffusion and interception tend to dominate collection of particles in uncharged filters. Impaction only really becomes relevant with lower efficiency filters, and in particular with the higher phase velocities and bigger particles being tested. And then this graph, this was published recently by some collaborators of ours. So this is just modeling those filtration mechanisms and producing a total efficiency, assuming they all act independently. And then on top of that, there's electrostatics. So if a filter is loaded with static charges, then they may capture uncharged particles by induced charge forces and charged particles by Coulombic forces. And that can be very significant. So in aerosol science, the science of particles suspended in gases, life would be very simple if all particles were just spherical and the same density, etc. But in reality, there's all sorts of complex nature of particles. And that gives rise, as well as the size dependence of filtration mechanisms, to different instrument techniques to classify them. The three major metrics are aerodynamic diameter and electrical mobility diameter and volume equivalent diameter. Don't worry about this equation. The take-home message here is that aerodynamic diameter is the metric of interest where particle inertia dominates, such as respiratory deposition, atmospheric lifetime and settling, and in particular, particle collection by filters, cyclones, and impactors. However, the industry standard technique for many years, in fact, since the 1970s, has been the differential mobility analyzer, which classifies by electrical mobility diameter. There, you have to charge condition your aerosol. It feeds into the top of this column, and the particles need to pass through a sheath flow as they're attracted by a rod held at a potential either positive or negative. Now, the drawback of this technique is, A, you're having to charge condition your aerosol, and you're only looking to pass singly charged particles, so you're having to reject all the particles that are not in that charged state. And secondly, as well as the singly charged particles of the size that you want for your testing, it will also pass larger, multiply charged particles that will have the same mobility. So there you have charging artifacts, multiple charging artifacts that would need to be corrected for. So very recently, there's a new technique that's been introduced. This instrument was launched in 2016. So instead of, it replaces the electric force in the DMA with a centrifugal force in two concentric spinning cylinders. So for a set ratio of centrifugal force to aerodynamic drag as particles move outwards in a spinning cylinder, you select the particle size you want. And the huge advantage of this is it doesn't depend whatsoever on the charge state of the particles, and the aerosol is truly monodisperse. You are only passing the particles of the size that you require for your filter testing. So a study we did previously, we were testing two face mask samples conforming to these standards here, and we were swapping in the two classifiers I've just mentioned back to back and comparing the penetration data. This slide just summarizes the operating set points. I think perhaps I'll leave that for people to go over. But it summarizes the size ranges of these classifiers. With the AAC moving into the microscale, the DMA will, particularly with various column designs, be able to classify down at the low sub-10 nanometer range as well. However, as you can see here, this graph shows for the same input size distribution from your aerosol generator, this is what's coming out of the classifier. And as I mentioned, this is showing the much greater transmission efficiency of the AAC. And this is primarily because you're not having to reject particles of any wrong charge state. The charge state doesn't matter. So that's data that's been done for both sodium chloride and DOS oil aerosols. And then this is the data for each classifier back to back on the same face mask. So you see generally they're in good agreement and the error bars overlap. And the specific circumstances where they don't overlap, here this includes higher DMA penetration result if the aerosol is drawn below the peak of the input distribution, and a lower result drawn above the peak. These are little clues that point to a possible explanation for what we're seeing. Then with DOS particles, this is a much larger input distribution extended into the microscale, so that's beyond the upper limit of the DMA, so the AAC can still cover that. And again, the penetration values for the DOS classified by the DMA are generally lower than those for the AAC. So the particle sizes lie above the most penetrating size of the filter, and the DMA output may contain larger, multiply charged particles. So to test that out, we took a cut with the DMA. This triangle plot shows the aerosol size distribution. We took a cut here, so these are the particles we want coming out. However, the doubly charged and the triply charged are being drawn over the peak, so they're going to emerge from the DMA as well. And then we scan that DMA output with the AAC. So here you see the singly charged particles of the desired size you want for your filter testing, but you're also getting these artifacts, the doubly charged particles and the triply charged, quite significant populations compared to the singly charged. And then this solid red line at the bottom is actually the other side of the N95 face mask sample that's being tested. So the triply charged particles coming out of the DMA are still visible even downstream of that face mask sample. So this points you have to be very careful with the DMA in interpreting its results, because the penetration data you get can be skewed by this presence of multiply charged larger particles. And then in a more recent study, obviously the pandemic motivated quite a lot of activity in the scientific community on assessing a range of face coverings and face masks. Obviously, regulated respirators, they're specified for inhaled air only, because this is for workers operating in contaminated environments. And the pandemic, the focus shifted more to the exhaled air to limit transmission of respiratory particles that may carry the virus. So we looked at a range of masks worn in healthcare settings and regulated PPE. I'll just draw your attention to the optical micrographs because they show what is key with the high performance of these filters is that the filter microstructure consists of an amorphous matrix, these randomly oriented fibers, the aim being to create very tortuous air pass through the filter to promote a high level of interaction between the filter fibers and the particles. And then face masks commonly worn in public spaces, community settings. So woven materials which have high breathability, but these regular grid-like perforations you see, while the fibers may be around 10 microns in diameter, they're bundled into yarns that are more like 100 microns thick, so that really limits the interaction of the particles with the filter. Obviously, later in the pandemic in the West, there were more cheap commercial options that came up with non-woven filter inserts to couple with the cloth coverings or otherwise non-woven polymer masks. And then this slide summarizes some of the key results from that, and you see this is a plot of the number penetration versus aerodynamic particle size, and they're very distinctly grouped into the face mask types with the woven fabrics. You see very high penetration on the sub-micron scale, only really coming down at several micrometers. The surgical mask and then the non-woven electric media, that means non-woven media containing static charges. So these are the regulated respirators here, FFP1 and P2 in EM149, and also a KN95, which is the Chinese standard. And then this same data is just reproduced on the right with a logarithmic y-axis to better distinguish the regulated respirators. So that's the FFP2 there. Cloth face coverings, okay, so these were some of the poorly performing ones, but which were still capturing most as you moved into a few micrometers in scale. The studies that have looked at the size distribution of particles emitted during breathing out tend to be multimodal, but the smallest one, these obviously water-based particles carrying biological material. They'll dry suspended aerosols and the modes will tend to be around a few micrometers. So as long as you're capturing most as you move into the microscale, it's still relatively effective. And actually see, these are for 3 different face velocities, and you can distinguish a separate filtration mechanism, inertial impaction, because you're actually collecting more as the face velocity is increased for those particles on the microscale. And then the filtration performance of the mask has to be balanced against the pressure drop or breathing resistance. So these are some pressure drop measurements for all those samples you have seen. And this is a method in the literature of just balancing, of quantifying that trade-off. So the filter figure of merit or quality factor, that's the log of the number penetration divided by the pressure drop. So that's just a way of ascertaining the overall value of a filter medium, balancing its filtration performance with its pressure drop. And again, the results are clearly demarked by the sort of groupings of face masks with the non-woven charged material types at the top. Just an important point to note is that the EM149, the regulated respirators, they're intended to be fit tested, so therefore a greater flow resistance can be tolerated. Obviously, masks with high flow resistance that don't fit so well will lead to significant leakage around the edges and potentially high particle exposure. Now, that fit testing was obviously not practical for the general public during the pandemic, so the lower pressure drop, greater breathability of the woven fabrics does at least mitigate some leakage around the edges, even if the material filtration performance is not nearly as good. And then moving on to HVAC, again, I'm sure members of the audience are familiar with some of the standards for air filters for general ventilation and the higher efficiency filters as we start to go into the grades that are more relevant to clean rooms and hospital environments. What we've done here, we've used the AAC to scan upstream and downstream of these HVAC media samples. So these are 2 examples for air filters for general ventilation. Again, you can see clearly in these penetration plots, this is for 3 different face velocities, where the middle one corresponds to the maximum rated airflow through the filter remnant, and then double and half of that flow. But you can clearly distinguish the action of 2 filtration mechanisms, diffusion, capturing the smallest particles, interception, the larger ones. As you increase the face velocity as well as more penetration, the most penetrating size shifts smaller because you're reducing that timescale for diffusive capture of particles, whereas interception is independent of flow velocity, so that's why you see the three data sets converge on that right-hand tail. On this lower grade filter, you can even see effective inertial impaction because at the higher face velocity, we're actually less particles are penetrated as we move into the microscale. Now, moving on up to the higher efficiency air filters, so H13 and EN 1822. The left-hand plot shows in gray the challenge. This is the input size distribution from the aerosol source. This is a Collison nebulizer for DOS oil aerosol. And then these three scans show what's downstream in the filter media sample. And then you divide the spectral density in the downstream by the upstream to obtain the graph on the right. So this is showing the particle penetration characteristics. It's just up to 0.05% by number. We then went up two more grades. So in the UL, starting to move into the ULPA category, U15. Here I changed the nebulizer to a mine-hard glass capillary, which that's given the highest number concentration I've seen from an aerosol source. This is 200 million per cubic centimeter. So we're throwing all that into the AAC classifier, which is fine. You just need to clean it a little more regularly. And then we're still, even with this very high filter grade, we're still able to obtain size information on what's emerging downstream. You can see on the WASC, this is going up to 0.01% at the top by number. And this red plot, that's corresponding to the maximum rated airflow for this particular filter sample. So that's just falling below the specified local penetration limit for that U15 category. And then again, as with the face mask, measuring the pressure drop. So a useful property of this trade-off equation that I've already shown for the face mask is that the value would be expected to be the same for multiple layers of the same filter. So the fact that the blue, red, and orange samples here have largely collapsed on the same line in this filter figure and merit plot implies very similar microstructures in those filter samples. And indeed, they're all consistent of glass microfibers. Whereas the green, which is sitting a little higher in terms of its trade-off between the filtration efficiency and pressure drop, that consists of electrostatically charged polypropylene fibers. So the loading of those charges in that filter medium has enhanced the particle collection without an associated pressure drop penalty. So just to conclude, the AAC provides a means to select truly monodisperse aerosol based on aerodynamic diameter, which is the most relevant metric for aerosol flow-through filters. And there's no need to charge the aerosol as with the DMA, the industry standard technique. So this removes any multiple charging effects and mitigates particle losses due to charging efficiency. And in the experiments I showed, the transmission efficiency AC was shown to be 1.5 to 5.5 times higher than the DMA across the particle size ranges tested. So that can be a very important factor where you're testing very high efficiency filters and you're trying to get a statistically significant downstream count to properly characterize and categorize those filter media. The 95% confidence intervals on the penetration curves from each classifier generally overlapped, and in the particular cases where they didn't, the likely explanation is the presence of multiply charged particles skewing the penetration data from the DMA. And then for HVAC filters, the data have shown that, again, the AAC would be very useful as a R&D development tool to help inform decisions during media development about the potential rated airflow and category for certification. And for face masks, I've covered regulated respiratories and all the way through to surgical masks and cloth masks commonly used in the pandemic. So that data showed that what's really important for high filtration efficiency is to create an amorphous matrix of fibers and promote a highly tortuous path for the aerosol flow through the filter. And with that concludes my talk. Thank you very much for your attention.
Wow.
I felt quite fast. I don't want to hold people up going home, so.
No. Really interesting. I'm still thinking. Does anybody have a question whilst I'm still thinking? Alan. So for the clean room, so you've developed an instrumentation. So in mobility analysis in the DMAs, you're suggesting now that there's an improved way for those in the filter manufacturing industry. That's where this comes from in terms of those, whether it's HVAC or respiratory protection, that there are more efficient instrumentations now than some of the traditional mobility analyzers we've been using.
Yes, I think, as I say, DMAs have been around for a long time, since the 1970s, so they're enshrined in a lot of filter testing standards, and this is a relatively new instrument. I think for the AAC to be mentioned as a classifier in the standards, it's just going to take a bit more momentum, because it's only been launched in 2016. Okay. It's already our best-selling instrument. We're sent to a lot of academic groups and people doing studies on aerosol particle properties. So the application to filter testing is a little more recent, something we've explored a little more recently. But yeah, the fact that you're not having to worry about the charge state for this method of classifying and removing all those complications and those need to correct for presence of larger multiply charged particles, potentially skewing filter penetration data, we see that as a big advantage for this instrument. So
practically then, does that present, there was so much data, I want to sit and read this with a lot more information, but with a lot more time, does that change some of our current view on the performance of particularly HVAC filters for clean rooms? But I'm also asking as well, because I'm interested in respiratory protection, is that some of that data, whilst it was more efficient in terms of the upstream to downstream, upstream concentration to downstream penetration, does it change the results? So if I've trended, if I'm a 3M and I've trended mask data for the last 50 years, does this now present me a different?
I think as long as data from DMA has been, I think the difficulty with the presence of the larger multiply charged particles is it's very much a question of what your input size distribution is. The size cut you're taking where it is relative to the peak, are you drawing those large particles over the peak and therefore there's a more significant population? And then relating that to the most penetrating particle size through the filter. So that's a scenario you've got to correct for in order to weed out a potential skew in that data. But I think most of the data showed the overlap was good in the 95% confidence intervals.
Okay.
I just highlighted various points where it was clear due to the particular size cut you're taking, where the multiply charged particles.
And so to us in a clean room, an H13 filter still can be considered that we are still buying H13 filters or H14 grade filters. There's no, you're not trying to change people's minds.
It sounds to me like H13 may be more efficient. It's actually very critical. Artificially discounting some of the molecules that are there that we can't. Artificially discounting some of the molecules, H13 may actually be more efficient in this technique than they are really than we're currently claiming.
That's true, yes. So if you're bringing in larger particles that are above the most penetrating particle size, it is going to artificially lower the penetration result and indeed make a filter perhaps look slightly better performing than it is. I have tried to quantify that for the particular experience we did on the text on the right-hand side there. Yeah. I mean, we have selected a worst-case scenario for this problem and illustrated it here. But it's, also in terms of generating size distribution of the DMA, the inversion techniques that are built in the software will be trying to correct for that. But again, there's a lot of examples where that will still degrade the data or skew the penetration result. So yeah, with this, the aerodynamic classification technique, that all just goes away.
All right. Any final questions? All right, very, very interesting. Thank you.
No, thank you.
Very, very interesting.
And,
all right.